Hello and welcome to another power system analysis class. In the previous class, we started with grids and how we manage grids and the importance of line capacitance and inductance and resistance and the role they play in grids. This week, we would start with capacitance and inductance of transmission lines and transmission line parameters. If we have time, we will continue with some examples and also resistance of a transmission line. These are very important because these factors determines the power flow and how much power we need, and also determines the transmission line factors and other parameters. So we will start again with line transmission and line capacitance. And for that, we need to first find the voltage difference or the voltage of a line. So the voltage difference between any 2 points, P alpha and P beta, is defined as an integral. So voltage of beta alpha is negative the integral of P alpha to P beta, E of dl. Now, in the previous example, the voltage difference between points P alpha and P beta located radial distance of R alpha and R beta from the wires is assuming sigma is equal to sigma 0. Therefore, V beta alpha is going to be equal to Q over 2 pi sigma 0 ln of R alpha over R beta. And this is where we assume that we have a circle distance of R alpha and R beta, which is the distance in the line in a transmission line. I'll explain that. With V beta alpha equal to negative integral of R from R alpha to R beta of Q over 2 pi sigma 0 R dr. It's going to simplify to Q over 2 pi sigma 0 ln of R alpha over R beta again. This is when we have a circle form. If Q is positive, then those points closer in have a higher voltage, and voltage is defined as the energy in joules required to move one coulomb charge against an electric field. So the unit is joules per coulomb or voltage. Voltage is infinite if we pick infinity as the reference point. Now, we had 2 points to measure the voltage. Now assume we have n parallel conductors. Instead of having one conductor and we want to measure voltage, for example, here, now we have n parallel conductors, each with a charge density of Qi coulombs per meter. The voltage difference between our 2 points, P alpha and P beta, is now determined by superposition, which is going to be equal to V beta alpha, which will be equal to 1 over 2 pi sigma of from I1 to N, Qi ln of R alpha I over R beta I. So it's a summation of all those that are in parallel with the conductor, where R alpha I is the radial distance from point P alpha to the center of the conductor I, and R beta I, the distance from P beta to the center of conductor I. If we assume that the sigma of I from 1 to n of Qi is equal to 0, then rewriting V beta alpha would be equal to 1 over 2 pi sigma of I from 1 to n, Qi ln of 1 over R bi, the same, this time Qi ln of R alpha I. We then subtract sigma of from I equal to 1 to n, Qi ln R alpha I 1, which is going to be equal to 0, and V beta alpha would be equal to 1 over 2 pi sigma, sigma of I 1 to n, qi ln of 1 over rbi, beta I plus 1 over 2 pi sigma, sigma of I equal to n, 1 to n of qi ln of r alpha I over r alpha 1. As we when we have p alpha when it moves to infinity, ln would be r alpha I over r alpha 1, which goes that one also to 0. Now, since the second term goes to 0, we will rewrite the equation, and in this case, v beta would be equal to 1 over 2 pi sigma, sigma of I from 1 to n, qi ln of 1 over r beta I. This equation holds for any points as long as it is not inside one of the wires. Now, this is a visualization of what we spoke about. Assume, so we have a three-phase, so we have 3 wires running in parallel for infinity with a fixed, and by the way, this is very important, with fixed distances. Assume we have 3 infinity long conductors, A, B, and C, each with radius r and distance d from the other 2 conductors. Assume charge densities such as QA plus QB plus QC equal to 0. Then VA is equal to 1 over 2 pi sigma, QA ln of 1 over R plus QA ln of 1 over D plus QC ln of 1 over D. So what we want to do is we want to find for this, for example, from the center and for each distance that we have. So we have a distance of D and another one. We have a distance of D and we have radius of R. Now, do you remember the equation for charge? What is Q equal to? Q is equal to CV. Yes? In other words, V is equal to what? Q over C. Correct? So, and the goal here, in other words, also C is equal to Q over V. What do you want to find here? We want to find capacitance between the lines. We want to know if we have 2 lines which run for infinity and they have a fixed distance between them, how much capacitance is between them. So we already have the voltage. We calculated it using the equations that mentioned. And it's simplified, by the way, to VA equal to QA, 2 pi sigma ln of D over R. So we have voltage, we have Q, we can find the capacitance between the lines. Now, for a single line, capacitance is defined as Q equal to CV. But for multiple conductors case, we need to use matrix relationship. And the matrix will be as follows. Q1 to Qn is equal to C11 to C1n and Cn1 to Cnn. Vi to Vn. In other words, we can write it as a matrix of Q equal to CV. So if we have 3 conductors, it's going to be Q1, for example, to Q3, C11 to C13, C31 to C33, and V1 to V3. Now, to eliminate mutual conductance, we'll again assume we have a uniformly transposed line. For the previous 3 conductor example, VA is equal to V. Since QA is equal to CVA, then C is equal to QA over VA. And we already know from that what was VA is QA over 2 pi sigma. It's going to be QA over 2 pi sigma ln of D over R. Okay? So we will replace VA with this. So C would be equal to QA over QA divided by 2 pi sigma ln of d over r. QA and QA cancel each other. So what we are left with is 2 pi sigma over ln of d over r. So as you can see, in the equation, Q is eliminated, so we don't even need to find Q anymore. What we need to find is just to find the distances, D and R, the radius and the distance between them, to be able to find the capacitance. Do you have any questions? Yes, exactly, yes. Epsilon or sigma or yes. Now, similar to what we did for determining line inductance, when there are n-bundle conductors, we use the original capacitance equation, just substituting an equivalent radius. And by the way, again, as you mentioned, sigma or epsilon 0 is 4 pi times 10 to the power of negative 7. Epsilon is going to be epsilon 0, depends on the insulator between them. That's the reason they put epsilon or sigma here. And but in long transmissions, that's air. So it's going to be the air insulator factor that we have. But for underground, and thank you for bringing that question, for underground cables, and sometimes they run for 50, 100, 200 miles, because the lines are so close, they usually use oil and inside with wraps to use as insulators. And for that, you can't use this equation, okay? That one requires a different, equation to measure the capacitance. This is, over the air, overhead, transmission lines that the lines are just separated by air, okay? And it's an estimate, and I'll explain what happens when you have very high voltage. This, works a little bit, but it's not very accurate, this equation. So similar to what we did for determining line inductance, when there are n-bundle conductors, we use the original capacitance equation, just substituting an equivalent radius. So RC of B is going to be R D1 2, D1 3, D1 up to D1N, and the power of 1 over N. Note for the capacitance equation, we use R rather than R prime, which was used for RB in the inductance equation. Now, for the case of uniformly transposed lines, we use the same GMR and DM as before. By the way, you don't need to memorize any of these proofs. That's just the final equations that we have. So C is going to be 2 pi sigma over ln of dm over RBC, where dm is going to be DAB, DAC, DBC in the power of 1 over 3, depending on how many lines we have. So this is going to be, if we have 4 lines, it's going to be DAB, DAC, DBC, DAD, and so on. So, but here, because we have 3 lines, and the lines are 3 phases of A, B, C, so we have 3 phases of A, B, and C. And this is, again, another reason that we put these in a triangle, okay? There are multiple reasons, but this is the main reason why usually we don't put it like this. And I'll explain what happens when you put it in a line. There's going to be a different capacitance compared to when you put it in a triangle, because the distances are going to be, the distance would be different. Now, RBC is going to be RD1 to D1N, 1 over N, and the epsilon or sigma is going to be for air. It's going to be 8.854 times 10 to the power of negative 12, or in other words, it's going to, if you can convert it also to the phi equation. And this is, again, for air. If you have an insulator, it's going to be completely different. Now, let's solve an example. We want to calculate the per phase capacitance and susceptance of a balanced 3-phase 6-series transmission line with horizontal phase spacing of 10 meters. So between each of these phases, we have 3 phases, we have 10 meters. Using 3 conductors, bonding with a spacing between conductors in the bundle is 0.3 meters or 30 centimeters between each of these. Assume the line is uniformly transposed and the conductors have a 1 centimeter radius. So line capacitance, if we want to find RCB, it's going to be first the radius of itself, which was 1 centimeter or 0.01 meter times the distance between each of these 3 phases, which was RAB and RBC, which is going to be 0.3 meters from phase B and phase C. And this is for itself. So phase A, phase B, and phase C. In a power of 1/3, which gives us 0.0963. dm is the distances we have between each of these 3 phases. How much are they? 10, and then you have another 10, and you have 20. And as you can see here, the equation was R D1D D12 to D1N. So it's going to be 10 times 10 times 20. It's going to be 1/3 times 1 in the power of 3, which gives us 12.6 meters. Now C is 2 pi times 8.854 times 10 to the power of -12 over ln of dm over r itself, which gives us 2 pi times 8.854 in times 10 to the power of -12 over dm over RCB. dm over RCB, it comes from this equation again. Now, if we do that, the capacitance calculated would be 1.141 times 10 to the power of -11 farads per meter. By the way, this is per meter. And if you want to find the susceptance, it's going to be XC is going to be 1 over omega C, which is 1 over 2 pi F times 1.14 times 10 to the power of -11, which gives us 2.33 times 10 to the power of 8 ohms per meter, which is a pretty large number. So again, this also depends on the frequency. If we have a DC system, it's completely different. Sometimes we can model, and we do that in smart grids that we see. We have a model system that it's called a DC coupled model, that we model in AC based on a DC, but we have a little bit of error. But to make it just simplify, we model AC as a DC. And when we do that, again, we neglect some of these parts. But majority of times, you're going to see that you're going to have a huge capacitance. Now, calculating all of this is difficult, and there is a reason. You don't know what material the wire is made out of. You don't know the purity of the material. You don't know how thick it is. So what the companies that produce the manufacturer does is they usually give you a table. It's called the ACSR table. And this table gives you the capacitance, the inductance, the resistance at different temperatures for different type of wires and code words that they have. They have different code words like flicker, hawk, hen, osprey, dove, eagle, peacock, and so on. And for each of them, at different temperatures, they have different inductives, and it's measured in ohms per mile, and capacitives, which is measured by mega ohms per mile, mega ohms mile. And this is from phase to neutral at 60 hertz. For 50 hertz, it's going to be different. And for different markets, they do put, different standards and so on. So if they're building for Europe, it's 50 hertz, it's going to be different. And They measure it in kilometers, so it's going to be a complete different, table. For inductance and capacitance, they assume a dm of 1 meter. So if you want to make it 10 meters, you have to just, add that to the equation. Now, let's continue that. So if we want to find the inductance, XL is going to be 2 pi FL or omega L. This is the inductance. It's going to be 4 pi F times 10 to the power negative 7 ln over ln dm over GMR times 1609 ohms per mile. And when we calculate that, we get to this point, these two equations. The first term is from the table assuming a 1 foot spacing. The second term is independent of conductor with dm in feet. And if we replace these numbers, we get to this point. We can, just replace them and find, using just this equation, we replace the numbers that we have for GMR and for inductance and capacitance per mile, and we can easily find it for like a 10-mile, 100-mile line with 10 centimeters distance, 1 meter distance, and 10-meter distance. So when you are calculating, you want to design a transmission line, you have these tables, you just replace them, and you can find how much inductance and capacitance you're going to have. And using those two factors, you can find the reactive power and design your power factor compensation system for it. Now, this is the principles that you need to learn. There are multiple softwares out there that you just put the distance. So they even have, the data sheets from the company. You just upload it. You say, oh, I want this using this model, and this is my distance. This is my the length of the cable, the diameters, and everything. And it will automatically generate how much capacitance. It's not going to be like 100%, accurate, but it gives you like 98, 97% accurate in a picture of what you're going to see in inductance, capacitance, and also resistance. And you can connect it to a generator and see how much you're going to get at the load. And you can give it, again, the information of your generator, and it will show you how much you're going to get at the load and how much loss you're going to have. So to use the phase to neutral capacitance from table, we use the equation that we had, 2 pi sigma 0 or epsilon 0 over ln dm over r. By the way, this is going to be equal to 1 over f times 1.779 times 10 to the power of 6 ln of dm over r. The first term is from table assuming a 1 foot spacing, and the second term is independent of conductor with the dm in feet. So this is the capacitance that we have, and this is the inductance or susceptance, better to say, for the previous one and the inductance. So this is XC and XL for the previous one. Now, for the previous one, we want to find it using the Dove example, and here we have a code word Dove, and we want to find it for this code word and see how it's done. Now, for this, GMR is 0.0313 feet. Outside diameter is 0.07725 feet. Radius is 0.03863, half of the diameter. And assuming a 1 foot spacing at 60 hertz, XA would be 2 pi 60 times 2 times 10 to the power of negative 7 times 1609 times ln of 1 over, because the spacing was 1, over 0.0313 ohms per mile, and XA would be equal to 0.420 ohms per mile, which matches the table for the capacitance. Now, for a capacitance, XC is going to be 1 over F times 1.779 times 10 to the power of 6, ln of 1 over R. which is going to be 9.65 times 10 to the power of 4 ohms per mile. So again, if you want to find the susceptance and capacitance and inductance of a system, you can use the table, just replace it, put it in this equation, and I'll give you the equation, and you can get the capacitance and susceptance. Now, you may ask, is there a difference if we have different wires? Okay. Majority of the wires that we use, 99% of the wires, do you know what material are they made out of? Why? Aluminum, yes. They are aluminum, and usually they have a small steel core as well to reinforce it, because as you know, aluminum is a little flexible. So if you put it on two poles with like half a mile distance, you're going to have sagging, okay? So you need to have a core that supports it. And the thing about AC, if you remember, if you have a cube, or if you have, imagine a pyramid or a cube, and you put AC electric charge to it, what happens to the charge? Or a circle. The charge goes to the edges. And it's the same thing that happens for AC as well. The higher the frequency, the charge wants to go to the edge of that. So if you put a steel core in the middle, it's not going to have a lot of effect on the resistance, because the majority of the charge is going outside. Same thing if you have a dome. I don't know if you had that in high school. You have these, charged domes that you put it had a belt running through it. It created, an electric charge, and if you touched it, you would see the sparks, and that's the principle of it. And there's another example as well. I don't know if you've seen some people wearing, these Faraday cage up, these meshed wire suits, and they connect them to high voltage, but the voltage doesn't go through their body. It stays on the surface. So AC signal wants to stay on the surface. So if you add that core, it doesn't make a huge. You may think it's gonna have a little effect, but not that much. And this is where ACSR comes from. By the way, I forgot to mention what ACSR are. ACSR is abbreviation for aluminum conductor steel reinforced. It has a aluminum shell. Outside is aluminum, and inside you have steel strand core. And another reason that we put steel, again, if you want to make the aluminum, to be able to connect to far distances, you need to make it thicker, and aluminum is very expensive. So another way to make it cheaper is add this, because you need a smaller diameter aluminum to have. So aluminum is expensive, and the thing that is more expensive than aluminum is copper. That's the reason we almost never use copper inside these transmission lines. It's going to be extremely expensive. So these are very expensive, but copper is way more expensive. So we limit using copper when we need like very high performance, the lowest loss, which is usually in a motor or an electric circuit. And the best conductor, do you know what the best conductor is? Gold. It's gold, copper, and then we have aluminum. There are new cables that are made out of steel. They are majority steel. I don't know, have you seen these new cables they have insulations that have black insulations, and they are twisted? They are actually made, majority, some of them from steel alloys. So they use less and less aluminum to make them cheaper. That's the reason you never see someone stealing some of those cables, because it's extremely difficult, to recycle and melt. But aluminum cables, if you leave it somewhere, someone will probably take it, because it's expensive aluminum. It could be easily melted. And now, typical transmission lines use multi-strand conductors. The ACSRs conductors are most common. A typical aluminum to steel ratio is about 4:1. Okay, so aluminum is about 4:1, and this table is for ACSR cables only. So if you have a different combination, it's gonna be a little, and depends on the purity of the aluminum as well. You may have different resistances and inductances as well. That's the reason the manufacturers they give you a table with each of these. And one batch may have a slightly different, parameters, but usually they have very similar parameters. So total conductor area is given in circular mils. One circular mil is the area of a circle with a diameter of 0.001, which is pi times 0.0005 square. And as you know, the area is going to be pi d square, so this equation comes from here. And this is in inches, by the way. What is the area of a solid 1-inch diameter circular wire? The answer is 1,000 kilo circular mils. Because conductors are stranded, and this is very important, the equivalent radius must be provided by the manufacturer. In tables, this value is known as the GMR and is usually expressed in feet. Okay, so GMR is the equivalent radius, which is provided by the manufacturer, and it's usually expressed in feet. Again, depend on the market. In Europe, they do it in meters. 1 feet is around 30 centimeters, so it's going to be a third of that. So line resistance. Line resistance per unit length is given by R is equal to rho over A, where rho is the resistivity. Do you remember what the equation for resistance was? It's rho L over A. So if of a circular, conductor, this is A, rho is the material or resistivity, copper is lower for, aluminum is higher, and L is the length. Now, why doesn't this have L? Okay, perfect, because it's per unit. So we want to find it per unit. That's the reason we eliminate L. Now, and what is the unit here? Meters. We want to find resistivity per meter. Therefore, we just find this resistance per meter. And when we calculate that, if we have 10 meters, you multiply by 10. If you have half a meter, you multiply by half a meter. Now, resistivity of copper is 1.68 times 10 to the power of negative 8 ohms per meter. For aluminum, is 2.65 times 10 to the power of negative 8 ohms per meter. Now, for example, what is the resistance in ohms per mile of a 1-inch diameter solid aluminum wire? 1 mile is 1,609 meters. So we have to convert that. And also, A, we want to find it in meters. So it's going to be 2 times 0.65 times 2.65 times 10 to the power of negative 8, because it's aluminum copper, over pi times 1-inch diameter. And we convert inch to meter. So it's going to be 0.0127 square meters and or centimeters, and then we convert it times 1609, which is conversion from miles to meters, and the result would be 0.084 ohms per miles. If we want to find it ohms per kilometers or meters, we don't have to do all these conversion. Since we want to do ohms per miles, we have to convert inch to centimeter, so we have to go to the metric system. Inches to centimeters or meters, and miles to meters and kilometers. Now, this is the thing that always confuses me. And the meter, mile, inch, feet, that's the easy part. But I still couldn't figure out Fahrenheit. Do you know how it is, like from Celsius to Fahrenheit? That's the most confusing one. Yeah. I just add 50 to it. So it's like 77, it's like 27 actually, but it doesn't work when the temperature goes lower. No, when it's 34, it actually is 0 degrees Celsius. So yeah. But these you can, estimate is like 1 mile is 1.6 kilometers, but when it goes to there. But in the exam, when it's a metric system, I'll give you the table so you know how to convert inch to. Inch is around 2.5 something centimeters. So now, because a AC current tends to follow towards the surface of a conductor, as I mentioned, the resistance of a line at 60 Hertz is slightly higher than at DC. Resistivity and hence line resistance increase as conductor temperature increases. As you know, the hotter it gets, you have the molecules are vibrating more, and the electrons and the electric field is more. It's going to become more difficult for it to pass. As conductor temperature increases, as mentioned, changes is about 10% between 25 degrees Celsius and 50 degrees Celsius, and 0.4% per degrees Celsius. But it's not linear. When it gets too hot, it goes up exponentially. And I'll give you the graph for it in the next slide. Because ACSR conductors are stranded, actual resistance, inductance, and capacitance needs to be determined from tables. Okay, so again, all manufacturers provide these tables, and it's going to help you with that. Now, this is the variation in line resistance, and you can see by time and by temperature how it's going to affect the system. The green one is after moving mean smoothing, and the blue one is after common filter. The time is in minutes. Input was 30 seconds ICCP data. Conductor resistance increased by 50%, indicating a 50 divided by 4, 125 degrees Celsius rise in temperature. So you can see it suddenly shoots up as well when you have higher temperatures. And after you have sagging, so it's, it gets very, very, soft, and you're going to have a lot of problems. I already showed you the problems that sagging may have. It's basically melting your wire. Okay. Now, this shows a 345 kilovolt plus transmission growth at a glance. And I just want to emphasize the importance of calculating the inductance, capacitance, and also resistance. And the higher the voltage you get, you have to be more careful. The problem is when you get to too much, voltage, a very high voltage, you need to have more spacing between the lines. You have to have thicker lines, and thicker lines means you have to have the poles the structures must be, higher up the ground, and you have to have, a bigger pole for the transmission line. It creates but it has a lot of advantages when you are transmitting in long distances. So this was 345 kilovolt transmission lines and 49. This is 345 kilovolts in 62, and you can see a huge increase, especially in the East Coast and Midwest. You can see Texas added. And then you have in the 70s, you can see that around the Great Lake areas, Chicago, and you can see how much it has increased. And in the West Coast, it's went from Seattle down to Los Angeles. And then at 94 and 2010, and it's still growing, especially with the growth of these data centers. And again, this shows the importance of these high transmission lines and a system that is able to manage and measure the capacitance and inductance. Ameren is the process of building a number of 345 kilovolt transmission lines across central Illinois. And this is a local part with the software. Locally, this includes a line between Sydney and Rising in Champaign County. And this shows a 345 kilovolt transmission line between Sydney and to Bondsville and Sydney to Kansas. You can see the pair of three lines, and Sydney to Rising. And this shows the Champaign, Urbana-Champaign part of grid. And if you look at these lines, you see, I don't know if you can see it, you see two lines on the top. You have three-phase lines, and you have two or, three phases going, and you have two lines on the top. Do you know what these two lines are for? And you can see it here as well on the top. So that's a thinner line that's used for lightning, and it's grounded. So if lightning hits, if it hits the transmission line, it's going to have a catastrophic. It's going to have a catastrophic. Sorry about it. It has it's going to destroy the transmission lines and transformers and generators. So lightning is a big problem for the system. Now, my pen stopped working. That's great. Now, additional transmission topics that we have, and this shows again the software that we have that are available that manages this system of the part of the grid, calculates the transmission line parameters and so on. Some additional transmission topics. We have multi-circuit lines. Multiple lines often share a common transmission right of way. This does cause mutual inductance and capacitance, but is often ignored in system analysis. Cables, there are about 3,000 miles of underground AC cables in the US. Cables are primarily used in urban areas. In a cable, the conductors are tightly spaced, or less than a feet, with oil impregnated paper commonly used to provide insulation. Inductance is lower, but capacitance is higher, limiting the cable length. That's the reason we just use it for city use. We don't use it in long transmission lines. Now, ground wires, the transmission lines are usually protected from lightning strikes with a ground wire. This topmost wire or wires help to attenuate the transient voltage currents that arise during a lightning strike. You can read faster than I, and actually my class is. The ground wire is typically grounded at each pole. And then we have the corona discharge. This is very important. Due to high voltages and the high electric field around the lines, the air molecules become ionized. This causes a crackling sound and may cause the line to glow. So if you put them too close to each other, it's going to create, sparks, and it's going to create a lot of problem. Actually, this corona effect is used to make ozone gas as well. There's what they call it a corona generator, that they use high voltage and converts oxygen O2 to O3 ozone. And I don't know how many of you have used a ozonizer. It's a device like small. You can buy one from Amazon, and it produces ozone gas, and it's used for odor elimination. So if there is a smoking smell or very bad smell in the car, leave it in the car for 10 minutes. And what it does is oxidate. Its main purpose is oxidation. When ozone comes in contact with anything, it's going to oxidize it, and it's going to neutralize any smell that it has. It's dangerous for human if you inhale it for long term, and it's going to after 40-30 minutes, it's going to turn back to oxygen. There are two ways that we know that we can create ozone. One is the coronal discharge method, and the other one is UV light. You can make it using UV. That's the reason we have the ozone layer. Anyways, so this is not always bad. Sometimes we use it for, but in high voltages, it's going to be very, very dangerous sometimes. Now, shunt conductance, usually ignored. A small current may flow through contaminants on insulators. And we have the DC transmission because of the large fixed cost necessary to convert DC to AC and then back to DC. I'm sorry, AC to DC and back to AC. DC transmission is only practical for long distances and specialized applications. It's only economically viable if the distance is above 400 miles or long cable power transfer, such as underwater, or if you want to connect two completely different grid, like Europe to, America. One, it has 60 hertz, like 120 volt or something, different voltage, different frequencies. If you want to connect them, it's easier to convert to DC, transmit it, and then convert it back to AC. They are getting a lot of traction in wind as well. So offshore wind, a lot of them, convert DC and transmit using DC because it's easier to manage the frequency. Because if the wind doesn't blow or blows very fast, you're gonna have different frequencies, so you can manage that if you convert it to DC. And these are the HVDCs, or high voltage DC lines, in North America. And you can see that all of them are between at least, two states with long distances. And again, to make it economically viable, it must be at least 400 miles distance. Okay, that's it for today's lecture. We're done with today's lecture. If you have any questions, just please let me know. We're going to have a review session this week, and next week we're going to have our first exam. Does that work for you? If not, I can put it on Wednesday. Monday is going to be your exam. Wednesday is going to be your review session, and we're going to go through some questions. Does that work for everyone? Do you have any exams? No? Okay. So I'll send an announcement online as well. Thank you and have a great day.